using dual rail encoding with micro cavities that feels like an opportunity maybe to push the easy button and suddenly be able to make a lot of progress. Let's see that. You're not seeing it. Okay. And I'll show you some results we're really excited about, where we can have orders of magnitude improvement in our ability to do single qubit gates, state preparation, measurement, and the like. And time permitting, tell you about how the idea of using erasures, which you heard from Jehan and which we learned from our collaborator Shruti Puri, may really make this a much easier and faster way to scale. Okay, so we've come a long way in superconducting quantum information from the first algorithms in like 2008, 2009. Now that these machines online with 10 or 100 qubits, single qubit gates can be pretty good. 2 qubit gates in the kind of 99 plus range. So there'll be a lot of times where like 1% or 100 keeps appearing in the top. So I'll kind of you can count how many times that. So 100. So what does that mean? Well, like if you have 10 qubits, you can do 10 gates on them. Or in terms of this metric quantum volume, I think the currently claimed record for superconducting devices is a volume of 512. But really, we should look at the exponent. That's 9 qubits. And so I sometimes half jokingly say, well, these machines are at least 10 times bigger than they should be. Okay. But the point is, we don't yet have quantum advantage, and we can't really scale because we need higher fidelity and we need error correction that really works. Okay? And that's why this is an important topic, an important workshop. Okay, so error correction, the beautiful idea. You say, well, I'm going to take a single bit of quantum information, I redundantly encode it. If I just had like bit flips only, I would only need 3 qubits. But already there's a downside. So 3 qubits, 3 kinds of bit flips. And actually the time to the first bit flip is now 3 times shorter. So this is what I mean by overhead. And this is why, you know, your error correction has to really work well for it to be worthwhile. Now, there's really elegant ideas, such as the surface code, which says we can make a 2D grid. If I measure the right weight force stabilizers, I only need sort of nearest neighbor coupling and everything. I can make something that's fault tolerant, not just to bit flips, but to all of the Pauli errors. The issue here is because there's more than one kind of qubit, now we're already up to dozens of qubits to make sort of the minimally functioning conventional code. On the other hand, there's this thing called the threshold. It says that we'll gain exponentially with the size of our patch once we're past the threshold. And the threshold is, wait for it, 1%. So we're getting close, right? But you don't really want to build this enormous machine with many, many qubits and just be like 1.2 past the threshold, or even a factor of 2 past the threshold. You'd like to be orders of magnitude past the threshold. And things really get good as you start adding more qubits and more redundancy. Okay, so this is our strategy that we've been pursuing for a while, and I guess a lot of you also. We're going to find a hardware efficient approach with the minimal overhead. We're going to use a system that has less types of errors and a longer lifetime, so it's going to have fewer errors overall. We're going to try and make distance 3, or sort of first order robustness, in the hardware level. We got to control the propagation of errors from the ancilla and our correction gadget. But then we can concatenate more efficiently once we're way past the threshold. So in a nutshell, the idea is, well, what if I could square my physical fidelity before I put it in the kind of conventional code architecture, right? And if we're at 1% now, if I could square it and go to 0.01%, then maybe I could beat the threshold by like 2 orders of magnitude. Well, then you really want to scale. By the way, this is always going to be a good idea, because let's say everybody doubles their coherences. This one will move 4 times further past the threshold. Regular one, 2. Okay, so probably there are a lot of experts, but like I said, not everyone is in the superconducting qubit community. So we like to use these 3D, or I'll show you some planar resonators. They have long lifetimes and really negligible dephasing. They really only have photon loss, as far as we can tell. And we're going to use the usual transmon as an ancilla. It's going to be the thing we use to control and measure our, our bosonic qubits, or our error-corrected objects that we store in the cavity. And the workhorse for this is this lovely dispersive Hamiltonian. You can have an off-resonant interaction between this microwave cavity mode and your nonlinear transmon. We can write it like this. The green transmon is a two-level system. We have our oscillator, and we have this chi dispersive interaction. It means that if the qubit changes its state, the cavity changes its frequency, which could look like dephasing, and that's bad. But also the transmon's energy, or its frequency, will be dependent on A dagger A, on the number of photons in the cavity. And so, like, if you put a coherent state or something in, you see a spectrum like shown here on the right. And for instance, if I want to make a projective measurement of n equals 1, just do a pi pulse on this peak here that's shifted over by chi. And after that, if I measure the transmon in the excited state, there must have been, actually now there is, one and only one photon in the cavity. You can also use this to create these crazy code states like cats and other sorts of things. And we can do actually arbitrary control. So if I take away the rotating terms and I add some drives on the qubit and the cavity, and I kind of throw that in a computer and I say, I want to do something. My clicker stopped working. I want to do something crazy like go from vacuum to, battery died, from vacuum to 6 photons. Computer says, play these microwave signals in the upper right here. And there'll be a funny thing that happens. This is the Wigner function conditioned on the state of the transmon. And at the end, the transmon, which started in the ground state, should have returned to the ground state. And I should have made n equals 6 in the cavity. You can also use the transmon to do a direct measurement of photon number parity and measure the Wigner function. And on the lower left is the measured Wigner function after we play that pulse. This is great. The catch is the whole thing took about a microsecond. That's the scale of chi. And during that time, my lovely cavity was entangled with this dirty transmon with its T1s and T2s. And so I will typically get something like 99% fidelity, another 100. Who's counting? Okay. And you can use this kind of interaction, and there's all sorts of really neat innovations and exciting things that have happened from the first break-even in 2006. You heard about the GKP and these amazing experiments from Vlad yesterday. But in all of these things, it's that nasty transmon that's really the limitation. Because, for instance, in this interaction here, let's say I'm trying to do a measurement of the parity in my cavity. If I have a phase flip on the transmon, that'll mess up the transmon state. And maybe I'll get the wrong answer in a measurement. But that phase flip kind of commutes through the whole Hamiltonian. This system of cavity plus transmon is error transparent to phase flips on the transmon. But remember, the interaction was like energy-energy. So if I have relaxation or heating in the transmon, if the transmon changes its sigma z, that imparts, if I don't know exactly when it happened, a random frequency shift and a random phase on my cavity. Yeah, it'll screw up any measurement, but it will also corrupt my bosonic logical. And this is really the mini version, the hardware efficient version, right, of the problem of fault tolerance. The act of measuring for errors had better not introduce more errors, or not too many errors, and it definitely better introduce no errors that are uncorrectable. That's death. So there were some neat ideas here about how to improve things. If we go from a 2-level transmon to a 3-level transmon and use GF as the things that we are going to couple to the cavity, then if we have relaxation, the transmon at the end will not return to G. If we see it in G in these gates, we typically would say, oh, that manipulation or that measurement or whatever on the cavity, that was successful. If we have dephasing, we might end up in the F state. And if we have decay, well, then we know that we had relaxation. And in some experiments that we did in our lab, using this really nice idea from Wenlong Ma and Zhang Zhang, if we could match exactly the dispersive shifts of the F and the E level, then it turns out we could do a gate where if you're in G, you succeed. If you're in E or F, you know the gate failed, but it didn't do anything to the cavity at all. So you just have to repeat it. And in this pretty hard experiment done by Phil Reinhold and Serge Rosenblum, they were able to engineer this matching of the chi's to do rotation on a binomial qubit around at least one axis. And we actually did the manipulation of the cavity state, detected Transmon-GEF, use that information to repeat the gate if necessary to make it deterministic. Might take a couple of rounds, but it's only failing like a few % of the time, so it's going to converge. And do interleaved randomized benchmarking, and we reached about break even for that operation on a logical gate on a single qubit gate on a logical. Because, okay, it was pretty tricky, the gate's a little slower, like there's overhead. So this GEF trick is really kind of a nice thing. But again, the goal was to find something simple, and we'll see that in a minute, and something which really allows us to take advantage of the long energy relaxation and even longer phase lifetime of these 3D cavities. If we have bare cavity, we cannot measure its phase noise. It's really vanishing. And in this experiment here, they're tuning the chi, and at this point, they sort of turn off the interaction with the transmon so that any change of its state or heating no longer introduces dephasing on the cavity. And you see that the T2 peaks up and goes almost to the green, which is 2T1, indicating that at least the bare phase lifetime of this thing was in the tens of milliseconds. And similar limits are placed from these other experiments, including labs. So we really want to take advantage of that. And so that leads me to this nice new idea. I guess it's my brand to steal from linear optics or cavity QED. So the dual rail encoding's been around a long time, and it's a great thing. It's what you do in linear optics, whether it's two waveguide modes or horizontal vertical polarization. But we've been recently realizing that if you do a dual rail encoding with two standing modes in these microwave cavities, it's a really simple and elegant system with a lot of nice advantages. So our logical code words now are going to be 0, 1, 1, 0. The photon's either in the left cavity or in the right cavity. And I claim the only thing that should happen is relaxation down to the vacuum state 0, 0. But that'll be detectable. I'll show you two different ways we can detect that. And this is kind of like the minimal bosonic code. Okay, you have to have two cavities, but you only have one photon. So in terms of like the overhead of how fast it goes and how many errors there are, we think it's kind of nicely optimal. Oh, and similar ideas also proposed in transmons. I think we're going to hear about those and maybe some experiments tomorrow morning from Amazon. So to make this into a thing you can actually manipulate, measure, etc., we still need a transmon ancilla. So the sort of building block here is going to be two of these cavity modes, a dispersively coupled ancilla transmon with the same old interaction. We're going to use 3 levels of the transmon, as we've figured out is a good thing to do. And that transmon's only going to have to interact with one of the cavities. You can put one on both cavities if you like. And then we just need to use a Josephson junction device and some parametric interactions like they do in the paramp community and lots of other places to turn on beam splitter interactions between the two. Okay, so here's a little attempt, and you can help me try and stay true to what I say I'm going to use. We were just deciding on this glossary sort of a few days ago. So in the error correction lingo, there's leakage, which is a transition out of the code space. And typically, well, and you don't know when it happened or where it happened. So in a regular transmon system, unfortunately, like the GE can not only relax or dephase, but it also can heat to the F state, and then things get bad. You've seen that in some of the surface code experiments. I'm going to try and use this term, decay error, to indicate the errors we get in the microwave cavity due to the finite quality factor. So photon loss is a decay error. If I don't know it happened, it's a leakage error. Then I'm going to use the term erasure error. Okay, and the purists will tell me that this is not a good term or not a good construction, because the definition of an erasure is an error that occurs at a known time and place. So when I was writing my thesis, I had these long arguments with my advisor about whether I could use the term DC current. He's like, it's direct current. True, but we all use the term DC current. And I want to talk about erasure errors. I'm gonna lapse, right? So it's not a proper terminology, but let's all call things erasure errors, which I sort of know. I don't even need to know what error occurred, but you know that qubit had an error right here, right now. It's often a leakage that I detect, but it doesn't have to be. For instance, you'll see my transmon errors can also be leakage. So similarly, a not quite correct term, but it's going to be really useful, especially for experimentalists like me, is erasure detection. An erasure is already detected, whatever. As in the lab, we're going to turn on a gadget. We're going to use an apparatus to check if an error has occurred. That's the act of doing erasure detection. Further, there's two kinds of erasure detection I want to distinguish between. And we're trying to get like the lingo straight between neutral atoms, for instance, and things here. I'm going to call it, but I'm not going to use the term all the time, end-of-line erasure detection, which is, for instance, in my dual rail, I could do a projective measurement, and maybe it tells me not just whether I'm in the 0 logical or the 1 logical, but whether I actually had any photons at all. And so I could learn in my measurement that an erasure has occurred. But I'm doing a projective measurement on the qubit. That's actually useful to characterize these qubits. And it's not really end of the line or not always post-selection, right? Because let's say I have a code and I'm using a dual rail as my ancilla. I want to measure that dual rail projectively, right? And it's nice to know if an erasure happened and then who it touched and all that sort of stuff. And then there's mid-circuit erasure detection, which is I somehow have a gadget that can tell whether I've leaked out of the code space, but it cannot tell me what the logical state is. It should ideally introduce no bit flips, no phase flips, no Pauli errors of any sort, but it won't be perfect. Okay, so good on this? Yeah. Okay, maybe. So, and please, you're going to hold me to it because I'm going to lapse, I'm sure. We are all sinners. So a nice thing about this dual rail is that we can sort of put what we think is the physics of these systems in and make a prediction of what kind of errors happen and how fast. And the leading thing, right, is photon loss, or maybe there's some finite temperature of my mode and there's a little bit of photon heating. That's usually 1% or 100 times slower. Those are going to be erasures, which are detectable in a variety of means, including a thing called joint parity that I'll show. Maybe things aren't perfect. There's cavities vibrating. There's some phase noise. Again, we think that's like tens of milliseconds or longer. Another thing that can happen is my transmon's in the ground state, but it heats and I don't know it. And that can introduce that bad back action of phasing. That's going to be typically like an order of magnitude or two longer, we think. And then there's like bit flips. This is also not quite the right terminology, right? But where I change between the two logical states, 0, 1, and 1, 0, when I wasn't trying. We actually, you know, there's basically only heating. You could have a second order process where you relax and then heat, but actually that's two things that are 100, and then the 1%, that's going to be third order in my 100. And actually in this thing, I think we can detect all leakage. Like if it goes to any crazy photon state, there's ways to actually do QND detection of that. So this would be really a very nice qubit. How do you do gates? Again, like a pi pulse is swapping a photon. I'm going kind of fast. Okay. Is swapping a photon from one side to the other. So that's what I'm going to call a beam splitter interaction. We do this by using RF drives. We can turn it on and off in nanosecond times. You can control the rate and the phase with which you swap. And importantly, I forgot to mention this before, one of the things we're going to do is we're going to have like the left cavity be 5 gigahertz and the right cavity be 6 gigahertz. Those are completely different frequencies, but the magic of this parametric interaction allows me to like swap a 5 gigahertz photon and some pump things that are classical into the 6 gigahertz photon in the other cavity. Why is that really nice? Again, think about bit flips. If we're not turning on these RF interactions, there's like no way a 5 gigahertz photon turns into a 6 gigahertz photon on its own. If there's any static coupling between those modes, it actually just goes into renormalizing the frequencies. So that's one kind of on-off. So I confess that we probably could have thought of this a long time ago, but at least on my part, I didn't allow myself to think of it because beam splitters were one of the harder things for us to do, at least in these high Q cavities with good fidelity. So a few years ago, we launched a couple of projects to explore this, to learn from the amplifier folks, from the experts in parametric processes like Joe and others, Mike. And we had a couple of them that actually succeeded quite well, almost with the same performance. I'm going to show you the one from this Liu et al. Reference that's there. So we have 2 cavities. I'm going to call them Arthur and B for no particular reason, Arthur and Beatrice. And so those are the poles, are 0, 1, 1, 0 of my state. If I load a single photon into one of those cavities and I turn on this parametric interaction, I see oscillations of the probability of finding that photon back in, B, not Bob. And it doesn't look like a usual Rabi oscillation. You see it's kind of falling down as the photon is lost. This is an important thing. We want this beam splitter interaction to not accelerate photon loss and to not introduce any photon dephasing because that would be bad. So photon dephasing is how it rises at the bottom. I can zoom in on those. You can see these nice swaps going back and forth between the 2 cavities. We can do this now in about 50 or 100 nanoseconds. And like I said, we can control the amplitude and phase, so we can make any arbitrary rotations, just like you would with a transmon, using these RF drives. And we can do things like randomized benchmarking. And if we do randomized benchmarking on this particular thing, we get a fidelity of like 99.92. But it's mostly limited by photon loss. So if in my measurement at the end, I can throw away the ones that are actually 0, 0, the fidelity improves by a factor of 4 in this experiment, going to 99.98 for all manipulations on the black. Okay. So single qubit gates work pretty well. Let's talk about Readout, because I want to confirm other things about this erasure qubit and how well it performs. So these days, one can do a very good projective measurement on a transmon. And if you have the 2 states G and E or G and F, you can distinguish them quite well. The main limitation here is that it takes about a microsecond to get good signal. And the transmon lifetime is like 100 microseconds. So there's like a 1% chance that it relaxes during the measurement. So the measurement fidelity is typically 99%. Actually, checking whether it's in G can also just be a thing that has very high fidelity, in the sense that it also doesn't need to change the state from G, doesn't need to excite the transmon. That'll be key if we're going to actually do checks on the transmon during the coding operation. And so, a problem here, though, is that, like I said, there's any single error or any single T1 event or relaxation during this thing will kind of limit the performance. And the nice thing here about the dual rail is that all the operations, as you'll see, are going to be robust or only going to fail when we have two errors. So if we have this dual rail, we have the two cavities. If I have two transmons, or if I swap in between and then do a second measurement using the one transmon, I can, for example, do this projective measurement on n equals 1 and ask, are you 1? And then I'm going to get 2 bits of information from my readout. And I can learn whether I'm in the logical 1 or the logical 0. I can also learn if I've leaked out, for instance, by relaxing to 0, 0, or by being heated to 1, 1. So this is an example of a projective measurement on the dual rail. And it includes, because of this extra bit of information, an end-of-the-line erasure detection. So here are the results of some recent experiments. We see this in a lot of systems, but what we've done here is tried to very carefully understand what limits these things. So the blue lines are a model where we put in a bunch of parameters and look at this. So now, we have potentially, 3 or 4 states that we could be in that we want to distinguish. And there's 4 potential outcomes here, even in a single round of these measurements. A key one is sort of errors that are bit flips. Those are in red here, where I misassign, let's say, the 1, 0 state as 0, 1. That constitutes an error in my measurement of the logical information at the end of the line. But that now requires 2 measurements to go wrong. So 100 becomes 10 to the minus 4. And then, we can prepare actually all the states. These are the 2 logical states plus the leakage states 0, 0, 1, 1. And we can quantify, for instance, if we have leaked, what's the probability that we misassign it to being in the code space. That's an important thing. That's going to be like 1%, because that's actually a single measurement. But if I'm going to run this thing where I only have a small probability of having been erased in the first place, that'll be 2 factors of my 100. I think being able to get 10 to the minus 4 level spam here is kind of unprecedented for superconducting qubits. I'm going to show you now some error metrology of looking at these dual rail qubits that I find quite remarkable. So I said there should be no bit flips. So let's prepare the 1 logical or the 0 logical, and then wait a certain amount of time. The sort of purplish thing here is the probability that this measurement says I've been erased. And that has a time constant where the erasures grow. That is sort of 400 or 500 microseconds here, the T1 time of the particular value. And you see the green and the orange here are like the probability that I prepared the 0 logical and I find it in the 1 logical. And if I zoom in here using this spam, this is with no normalization, just counts. 10 to the 5 counts, and 4 times in 10 to the 4, it's wrong in the beginning. And then if I delay, this is 20 microseconds, it goes up by sort of 1 part in 10 to the 5 per microsecond. And a lot of the things I'm going to show you here are not simple exponentials. And so take the times with a grain of salt. I think actually the probabilities in a short period of time are more interesting. This is actually limited here by the misassignments of the erased states. So it's only a bound. Our apparent erasure rate is something like, 1 part in 10 to the 5 per microsecond, or effectively 80 milliseconds. Other measurements we can do, we measure that the actual thermal population of cavities here is like 10⁻³ or 4. So the actual bit flip of relaxing down and heating back up should be minutes. By the way, this is 1 round of measurements I'm showing you here, because you can do this check on the cavities in a microsecond. and learn a bit of information. You can also do multiple rounds of the multiple measurements and get even better stuff. Is this thing coherent? Let's do a Ramsey experiment. So we create one photon in one of the cavities. We do a pi/2 pulse with a 50-50 beam splitter. And then in the top plot are the inferred results of this 2-bit measurement at the end. The 0 zeros grow. That's just the lifetime of the cavity. That's the K. That's what sets this green envelope here, and the orange and the green here are the sort of Ramsey oscillations due to the finite detuning we've introduced. But we can do this end of the line erasure detection and try to see what the actual phase flip time is, and it's longer. And you see we can even look in on sort of microsecond timescales with 3 and 4 digits of resolution. So the dephasing time here is longer. There are other mechanisms we're not yet controlling for. For instance, there's a no jump back action due to a difference in the cavity lifetimes, which should come out perfectly when you do an echo. So if we do an echo experiment, you see the following. Again, the solid lines are a model with only 1 or 2 adjustable parameters that tell us what we should see, one of them being the phase lifetime. I find this just remarkable. So 0 time on this zoomed in plot is state preparation, pi/2 pulse, wait 20 or 50 nanoseconds, pi pulse, pi/2 pulse, and measure. The total error of that is 0.25%, 99.75% fidelity. And then over 20 microseconds or 10 microseconds, it decays by another couple of parts in 10 to the 3. This is only like 3 milliseconds. Again, we think that the end phase flip lifetime here can be much longer. So that tells us this dual rail is pretty handy. If we want to check for erasure and keep the qubit alive, what can we do? Well, we want to know, are we in like 0, 1 or 1, 0, or did we heat to 1, 1 or relax to 0, 0? We want to know the joint photon number parity. Is the sum of the photons in ART and B even or odd? But don't tell me whether it's in ART or B. Can't do that. And it turns out that even if you have just a transmon here coupled to one cavity, if you drive this beam splitter between the 2 cavities in the right way and for the right amount of time, you will swap the photons and swap them back. And the transmon, as it is wont to do, will have a phase shift that's dependent on the number of photons that were in the swapping thing. And if you do that with GE and F, then the F state tells you whether you've had an erasure in the cavity, and E tells you whether the transmon relaxed. And so both of those are detectable erasures. So here's some stuff from my lab where we're going to do this echo experiment to measure the coherence of the dual rail. And we're going to stick in this dark blue box, which is an echoed erasure check, because the erasure might put a deterministic phase in and it takes it out. So it's 1 round of the joint parity pi pulse and another round of this joint parity. Each of these in this first implementation takes about 5 microseconds, with maybe 10 microseconds for the whole thing. And this is a different system with a snail coupler and some shorter lived cavities. But if you look at the post-selected thing, you have an average cavity lifetime here of 200 microseconds. That's the black line. If you measure the post-selected T2 with end of the line or echo with end of the line. But now if we add 1, 3, or 5 of these mid-circuit erasure checks, the contrast in our Ramsey experiment goes up. So I'm not yet ready to quote exact numbers on the fidelity of this and the back action of this and how much it does introduce a Pauli measurement. Stay tuned for that coming soon. And this is very much inspired in trying to parallel the really beautiful things that have been done in neutral atoms with erasure detection and the idea of how powerful that is for error correction from our colleagues. So that joint parity, by the way, is the ingredient that you need to do a 2-qubit entangling gate. If you now do joint parity between the neighboring elements of 2 dual rails, that will impart a phase which can be arbitrarily controlled by the Transmon phase. That one you can also, that should have the Transmon returning in G. So both Transmon T1 and T2 during that operation, which should be 1% of the time, can be detected, and we can characterize those as erasures on both of the qubits that were involved. So we think we have all operations, single and 2 qubit, and a mid-circuit erasure check, which are all robust, or at least we can have a 1% or so chance of assigning them as failed or as an erasure. And these are some simulations about what could happen as a function of various coherences in the system. The important thing here is that the reds and the blues are like the probability you have one of the errors, but you will detect it with sort of 99% efficiency, 100. And the double errors here are going to be in the 10 to the -4 or lower range because it's the square of 100. And if we miss some of these, that's also going to be on the same. And the reason this is important in the larger context of error correction is this understanding now that even in circuit-based systems, it's really nice if you can have erasure errors and Pauli errors. And if we can arrange for the erasure errors to be 1% and the Pauli errors to be double errors or single errors that I missed, they'll be double errors, they'll be 100 squared, then this is really nice and really powerful, perhaps, for putting this into a larger code like the surface code. And so again, in this work from originally from Jeff Thompson and Shruti Puri, they sort of looked at neutral atom system, and if you have Pauli errors, the threshold's like 1%. If you have only erasures, the threshold goes up to like 4 or 5% per gate, and then we can look at sort of the mixture of these. The other thing that's important here is beating the erasure threshold by a factor of 10. Since it scales as D, not as D over 2. Oh, Shruti's making the poopy face. This is not quite right, but it scales faster. So let me say that being a factor of 10 past the erasure threshold and a factor of 100 past the Pauli threshold seems kind of optimal and feasible. So here are some simulations with those kind of probabilities. This is for 1 microsecond 2 qubit gates and erasure checks, which we think is doable, and sort of today's kind of coherences. So if you had 1% erasures and this 10 to the -4 Paulis, you gain as you went from distance 3 to 5 to whatever, factors of 10 to 100. That'd be something really worth scale. And we think you can do that. Actually, you only need coordination number 3 for your cavities. And if you compare it to, let's say, like the Google architecture, I think it's 1 more Josephson junction device per unit cell than the typical thing. It's 2 cavities, but those are you make. And before everybody rushes out and buys futures on large blocks of high purity aluminum, there are other and more compact ways to do this. Here's a recent result from my student Suhas. These are tantalum strip line resonators in this little hairpin that go in an aluminum tube. They have in the first 4 devices 1 millisecond T1s and 2 millisecond T2s. They're combined with a little Transmon and Readout all in a single chip. And oops, sorry, I think my little reference to that got removed. So my recently graduated student, the Priceman, has another way of making a sort of quasi 3D thing. Oh, it's down here. Okay, so I think it's time for questions. I want to thank the combined team. It's really great to work with brilliant people. The dual rail looks really interesting. It's kind of optimal. For me, it's like sort of the Transmon moment of quantum error correction. Like all of a sudden you needed only 1 junction, things were simpler. It didn't seem like you gave away really anything except the anharmonicity, but it was only enabled by RF measurements and here by the high fidelity beam splitters. Maybe we can hit soon the goal of going from 1% to 0.01%. And the initial experiments here look kind of exciting, and stay tuned for more. Thank you.
Thanks for that beautiful talk. Does anyone have any questions?
So the dual rail encoding is so exciting for, or so useful for optics because optics doesn't have very many tools. And a single photon is basically the only state with negativity we can produce easily. You've got a lot more control than that. So do you think that you might be able to use that to do something that's a little more sophisticated than a simple dual rail that could get you further? For example, 0 anything plus anything 0 still has the same type of heralded erasure out. Anyway, it's kind of an open question. There might be more for you to play with.
Yeah, I mean, so indeed, I think one of the important things I should have remembered to say this is like, in comparison to linear optics, we can deterministically create and measure the single photons with like 99% fidelity. So even when you're doing these erasure things, it's succeeding most of the time. Yeah, I think there's a lot more things you can do. And of course, 0 anything plus 1 anything, you could do this in a transmon. Now, the transmons have as much dephasing as T1, so that's why I think the cavities should win in the end. I also think you can always make a cavity longer lived and with lower dephasing than you can make a Josephson junction thing. So that's kind of our thing. But there's definitely a lot more you can do, and applications of this and things like remote entanglement. The idea that you get a do-over if you get it right 99% of the time. I mean, who wouldn't like to have that called a perfect grade, right? So.
I'm just waiting.
Hello.
Oh, yeah.
Hey.
Yeah, hey, thanks for the very nice talk. I have a perhaps somewhat naive question. So the dual encoding, the things that you're talking about, is effectively a bosonic quantum error detected code.
Yes.
So they also have, yeah, sure, you can, in principle, like inherit a lot of the glossary from quantum error correction, lingo, and so on. I was wondering, before you scale up to try to put these dual qubits into a surface code or something like this, are you thinking about doing any experiments or simply putting it into a quantum error detecting code?
Yeah. So having orders of magnitude separation between the various kinds of errors, at least idling, as I showed you, not necessarily bias preserving and all the gates and all that stuff, I think does mean that small codes can really help. You can do error detection codes. We can do an error detection directly, right? This joint parity thing. You can do an erasure code. There's various small codes now which are much more likely to be beneficial. And so I really like the idea of being able to, climb your way up rather than having to jump into doing 50 things at once. Yeah. Oh, yes.
Hello? Oh, hi. Sorry, perhaps a bit of a naive question. When you were talking about the mid-circuit erasure checks, was there any sort of correction going on there? Was it like, because I saw your fidelities went up with the amount of checks that were done. Is that just by post-selection or is?
Oh, sorry. Yeah. In this experiment, we are collecting the information as we go. So like during this 1 millisecond, there are 5 measurements and we learn the result of the measurement like right away in the middle. In this particular experiment, we're not doing anything in real time with that information. We're just logging it. And one reason it gets better here is like if you had 5 votes that say it didn't get erased, it's much more likely that it didn't get erased, right? But the point is you can use that information. Like, for example, in the surface code, you would want to, say, oops, and reset.
Okay, thank you.
Yes, very impressive results. I was wondering, do you see any deviation from idealities? Like, is 10 to the minus 2 square always 10 to the minus 4?
I'm sure, right? I think, for example, in the post-selected single qubit case, it only improved by a factor of 4, right? And that's because there are still things like heating of the other elements and so on that weren't fully taken, right? So I think, there definitely can be non-idealities. The fact that the beam splitters work and preserves the noise bias is again, the key that unlocks all this. So, we'll see.
It must be hard to detect, right? But it's like for
Well,
instance, yeah.
Hard to detect, but sort of not, right? Because like we can do really metrology on things. So, we are doing the 2 qubit gate, that's in progress. And like, we think we can detect errors down to like the 10 to the minus 4 in that gate when post-selected. So we'll see. That's part of the point of this measurement stuff too, is to say we really have metrology and know what we're measuring. Okay, so they're gonna give me the hook.
Thanks, Rob.